Matrix multiplication, prior to this we've added and subtracted. With adding and subtracting, matrices needed to be the same size. To multiply matrices, you guys just did a pattern and found out when it was possible to multiply them. And we'll say they have to be compatible. The columns in the first matrix must equal the rows in the second matrix. In other words, the middle numbers, if you have a 2 by 3 and you're multiplying it by a 3 by 5, these middle numbers need to be the same. If they are the same, we say they're compatible and we can multiply them. You also saw in what we did before that the answer that you get comes from those outside numbers. The answer would be of size 2 by 5. So here, these middle numbers are the same, and the size of your answer comes from the outside numbers. So this is just the logistics and the structure of when something is possible and how big the answer will be. Next, we start to look at the rules for multiplying. So rule 1, the middle dimensions must be equal. So here we have our 3 by 2, and here we have a 2 by 1. Since these middle numbers are the same, we can multiply. There's rule number 1. Are the middle numbers equal? Yes, they are. Here, we have a 2 by 2 multiplied by a 1 by 3. The middle numbers are not equal, so this one will not be possible. Rule number 2. If we can multiply them, then the answer will have the dimensions of the outside numbers. So here we have our 3 by 2 multiplied by a 2 by 1. The answer matrix is a 3 by 1 coming from the outside numbers. So since the middle numbers are the same, we can multiply them, and the answer will be the outside numbers. So we'll have 3 rows, 1 column. And then to get the answers in the matrix multiplication, we multiply a row by a column and then add. So what does that mean? Okay, I'm going to color code things here. I imagine if I want to find in my 3 by 1, so we know that our answer is a 3 by 1 because we started with a 3 by 2 and multiplied by a 2 by 1. If I want the item in row 1, column 1 in my answer, I need to take row 1 and multiply it by column 1. So this is what I imagine. I've got row 1 with 1, 2, and column 1 with 7, 8. This is what goes through my head. I don't know if you like the visual, but I imagine this 1 and 2. Oh, I want just this for now. Okay. There we go. Are you ready for the visual? Okay. I imagine this 1 and 2. I take it, I rotate it so that it matches up with those numbers, and then I go, boom, and I blast it into those numbers. So what happens is, whoops, right, there we go. See, the 1 hits the 7, the 2 hits the 8. 1 times 7 is 7, 2 times 8 is 16. Then all the remnants that fly out of that multiplication, you gather them together, add them up, and that becomes the 23. If I took, put that one back, different color. The 3 and the 4. I took that one, rotated it, boom! The 3 hits the 7, the 4 hits the 8. 3 times 7 is 21, 4 times 8 is 32. 32 plus 21 is 53. Whoa. Sorry, there we go. I just wanted to get rid of that. And finally, if I took the 5 and the 6, rotated them, boom, right through. 5 times the 7 would be 35. 6 times the 8 would be 48. 35 plus 48 is 83. And so the position of the answer, right, this one right here is in row 3, position 1, tells me I need to take row 3 and multiply it by column 1. Row 3, column 1, take row 3, multiply it by column 1. And we get all of our answers that way. Oh, there's my 3, 4. So again, some more preliminary stuff. If the middle numbers are the same, you can multiply them and you know the size of the answer. If the middle numbers are not the same, you can't multiply them. Can we multiply A times B? Yes. So I would like you to get the answers for each of these, and then I will put them up in a second. I can help you find out where that mistake is. So here's the answer to the first one. Check how you're doing on BC. 6, -8, 1, -14. So there are the rest of the answers. And like I was talking before, the question came up for F. Some people took the answer that they got in A, which was AB, and then multiplied that by C. And then somebody else said, well, what happens if I took the answer I got in the second one, and if I multiplied A times BC? Would those answers be the same? And someone tried it and found out, yes, they got the same answer. But what this leads to is us asking, what are the properties of matrix multiplication? Okay? We notice that unlike regular multiplication, A times B, here's A times B, here's B times A, they're not the same. So reversing the order of things doesn't yield the same result. Now, in mathematics, we call that property commutative. If you could do 5 times 3 is the same as 3 times 5, regular multiplication is commutative, but matrix multiplication is not. So if we go to list the laws of matrix multiplication, that first one shows up that A times B is not the same as B times A. It's not commutative. But what we did notice is if we have 3 things multiplied together, you could do A times B first and then times by C, or you could do B times C first and then times by A. The mathematical word for that property is associative. You can distribute matrices. Now, I don't know why you would want to do this, because if you distribute, you'd have to do A times B and A times C and then add them. Or you could just add them first. Do you remember how easy adding matrices was? You could do that first and save yourself some time and then multiply by A. But if you wanted to, you can distribute. And we talked about the identity matrix, that there's something in identities that's like multiplying by 1. Those were all those 1s on the diagonals with 0s everywhere else. In fact, Here's one of those ones. 1, 2, 3, 4. Look what happens. Row 1, column 1, you just get the 1. Row 1, column 2, you just get the 2. Row 2, column 1, you would just get the 3. Row 2, column 2, you just get the 4. So we have something called an identity matrix, which acts like multiplying by 1. And a key thing that we're going to be looking forward to is the idea of an inverse matrix. And when you multiply a matrix, if that's my matrix, if I multiply that by my inverse, I get my identity matrix. It's sort of like an inverse is kind of like dividing. You divide it out, you get 1. So what would this be? What could I possibly put there so that I get 1, 0, 0, 1? And so we'll learn techniques for finding inverses.